Have you ever wondered how your phone can pick up even the quietest whisper and make it perfectly clear? Well, the secret is a tiny little component called a MOSFET, and even more importantly, a really clever trick we use to understand it. Today, we're going to pull back the curtain on the difference between large signal and small signal operation. This is the key, really, that unlocks the entire world of amplifier design. So let's dive right in. Here's how we're going to break it down. First, we'll tackle the amplifier's dilemma. Why a transistor needs a sort of wake-up call before it can do any work. Then we'll figure out how to measure its strength. After that, we'll get into the two secret languages it speaks and master a simple two-step process to understand its behavior. And to wrap it all up, we're going to bust some common myths that trip up even seasoned designers. All right, so let's start with the most basic question of all. How do we get a single transistor to actually amplify something? You know, if you take a microphone and hook it up to a transistor that's just sitting there, what do you think happens? Absolutely nothing. It's kind of like a car engine. The engine needs to be idling before you can hit the gas and go somewhere, right? Well, a transistor is the same way. It needs to be biased, given just enough power to get it ready for action. Think of it like a calm river. If there's no water flowing, you can't really make any waves. For a transistor, that flow of water is a steady DC current. Without it, your audio signal, your little AC wave, has nothing to ride on. So we have to apply some DC voltage to get that current moving and create a baseline for our signal to do its thing. So how do we get that DC voltage set up correctly? You might think, hey, why not just hook up a battery? But here's the problem. A battery gives you a constant, unchanging voltage. It's like trying to make waves in a frozen lake. It's just not going to happen. Your signal gets completely flattened out. The right way, the way we do it, is to use a resistor with our supply. That resistor acts like a gatekeeper for the current. It gives us the steady flow we need, but it also gives our signal room to make a splash. And the whole goal of this setup, the whole point of biasing, is to get the transistor into its sweet spot. We call this the saturation region. I want you to think of it like a super responsive faucet. When you're in this region, a tiny little turn of the knob, that's your gate voltage, gives you precise, linear control over the flow of water, which is your drain current. And that precise control, that is the magic we need for amplification. Okay, so we've biased our transistor, it's on, it's in saturation, it's ready to go. But how good is it at amplifying? How strong is it? That brings us to what is arguably the single most important parameter for an amplifier. It's transconductance, or as we call it, GM. Transconductance, or GM, is the ultimate measure of a transistor's strength. It literally tells you, for this much change in input voltage, you're going to get this much change in output current. If you look at the device's characteristic curve, GM is simply the slope at our operating point. A steeper slope means a higher GM, and that means a much stronger amplifier. It's that simple. Now, this is where it gets really interesting. It turns out there are three different ways, three different recipes, if you will, to calculate GM. They all give you the exact same answer, but they come at it from different angles. One focuses on the transistor's physical size, another focuses on the current you're pushing through it, and the third looks at the extra voltage you're applying. But hang on a second. If you look closely at these equations, you might spot a problem. The first one says GM is proportional to the overdrive voltage, right? But the second one says it's inversely proportional. So what gives? How can they both be correct? This is a classic point of confusion, but the answer is incredibly important for any designer. The secret, the key to the whole thing, lies in asking one simple question. What are you holding constant? See, if you have a single fixed transistor on your breadboard and you increase the overdrive voltage, your current goes up, and yes, your GM goes up. The first equation works perfectly. But now put on your designer hat. Let's say you have a strict power budget, so your bias current must stay constant. Now, if you want to increase the overdrive, you're forced to use a physically smaller transistor to keep that current down, and a smaller transistor has a lower GM. It all depends on your constraints. All three formulas are correct. You just have to know which one applies to your situation. This brings us right to the heart of our discussion today. We've got this transistor, and we know it has this complex, nonlinear behavior. So how on earth do we analyze it in a real circuit without pulling our hair out? This is where we draw a line in the sand between the full, complicated reality, what we call large signal operation, and a really clever, really powerful approximation called small signal operation. Here's an analogy. Imagine trying to predict the exact path of a single water molecule in the middle of a raging waterfall.
That's kind of like the large signal model. It's incredibly complex, but it's the total truth. Now, imagine you don't care about one molecule, you just want to know which way the water is generally flowing. That's the small signal model. It's a simple, powerful approximation that gives us the answer we actually need without getting lost in the weeds.
So here it is. This is the full story of the transistor in saturation. And you see that little squared term on the end? That's the villain of our story. That's what makes this equation nonlinear. It means that if you double the input voltage, you don't just get double the output current. This nonlinearity makes the math really, really messy. So how do we get to use our simple approximation? What's the catch? Well, we have to follow one rule, the small signal condition. And it's pretty straightforward. It just means that the AC input signal, the little wiggle we're trying to amplify, must be much, much smaller than the DC overdrive voltage that we use to bias the transistor in the first place. And look at the payoff. This is why we do it. If our signal is small enough, that complicated square law equation magically simplifies into this beautiful linear relationship. The total current is now just our original DC bias current plus a small signal current. And what's that signal current? It's just our input voltage multiplied by a constant. And what's that constant? Our good old friend, GM. The nonlinearity has vanished. Now, this simplification isn't just a neat math trick. It's so powerful that it gives us a practical step-by-step procedure that we can use to analyze pretty much any amplifier circuit you can think of. Here's the playbook. It's a classic divide and conquer strategy. Step 1, DC analysis. You pretend all the small AC signals don't exist, just set them to 0. Then you use the full large signal model to find the circuit's DC operating point. This is also where you calculate the value of GM. Step 2, AC analysis. Now you do the opposite. You kill all the DC sources, you ground them, and you replace the complex transistor with its super simple linear small signal model. And finally, step 3, superposition. The total behavior of the circuit is simply the DC part from step 1 plus the AC part from step 2. It's incredibly elegant. Okay, this two-step method is fantastic. It's what we all use. But it also leads to a very, very common misunderstanding that we really need to clear up right now. Here's the trap that so many people fall into. They start to think that large signal just means DC. And that is not correct. It's only half the story. Yes, we use the large signal model for all of our DC bias calculations, but, and this is the important part, you also have to use it anytime you're analyzing an AC signal that's too big to be considered small. So let's make this crystal clear, once and for all. The large signal model has 2 jobs. Job number 1, all DC bias calculations. Job number 2, analyzing any AC signals that are not small. The small signal model, our little shortcut, it only has one job. Analyzing AC signals that are small. That's it. If you remember that, you'll avoid a ton of confusion. So the next time you hear that perfectly clear voice coming from your phone, you'll know the secret behind it. A tiny transistor working in its sweet spot, analyzed with the power of the small signal approximation. Now that we have this tool in our belt, a whole universe of circuits is opened up to us, from high-fidelity audio gear to life-saving medical instruments. The possibilities really are endless.